June 13, 1944, Dymchurch, Kent. The sound hit first, not the scream of a Luftwaffe bomber or the whistle of falling ordnance, but something entirely new. A mechanical pulse, like a two-stroke motorcycle engine magnified 1,000 times, hammering across the night sky at 400 miles per hour. British anti-aircraft crews stared upward into the darkness, listening to that distinctive buzzing roar grow louder, then abruptly cut out. 7 seconds of silence. Then the explosion. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The V-1 flying bomb had arrived, and suddenly every assumption about air defense was obsolete. You couldn't intercept what you couldn't see. You couldn't hit what moved faster than any bomber. And you definitely couldn't stop an unmanned missile that didn't care about searchlights, didn't need a pilot, and arrived without warning in the middle of the night. That's where our story begins. In the collision between German vengeance weapons and an American radar system that nobody outside a handful of engineers at MIT even knew existed. The SCR-584 wasn't just advanced, it was revolutionary, and for the Germans launching their terror campaign against London, they had absolutely no idea what was tracking them from the ground. The mathematics of the problem were brutal and unforgiving. A V-1 flew at roughly 370 to 400 miles per hour, depending on fuel load and atmospheric conditions. At that speed, the missile covered about 600 feet per second. Traditional anti-aircraft fire required visual acquisition, manual tracking, and mechanical computation of a firing solution. By the time a gunner spotted the target, calculated its trajectory, and fired, the V-1 had already moved hundreds of yards from where the shell was aimed. Hitting one at night without visual reference was statistically impossible using conventional methods. The British had been refining anti-aircraft gunnery since 1939, learning hard lessons during the Blitz when Luftwaffe bombers pounded London night after night. They'd developed the gun-laying Merc II predictor, a mechanical computer that calculated firing solutions based on visual tracking data from optical range finders and height finders. Crews would manually track a bomber's position, feed that data into the predictor, and the machine would compute the necessary elevation and azimuth for the gun. It worked reasonably well against Heinkel and Dornier bombers cruising at 180 miles per hour and flying relatively straight courses. But the V-1 wasn't a bomber. It was faster, smaller, and flew an unwavering trajectory programmed by a simple gyroscopic autopilot. There was no evasive maneuvering, no pilot adjusting course, just a tiny cruciform shape hurtling through the sky at speeds that made visual tracking nearly useless. British Anti-Aircraft Command faced a crisis of capability. The V-1 offensive, codenamed Operation Rumpelkammer by the Germans, began on June 13, 1944, exactly 1 week after D-Day. Hitler had promised his generals that the Vergeltungswaffe, the vengeance weapons, would turn the tide of the war. The V-1 was the first to arrive, launched from fixed ramps in the Pas-de-Calais region of occupied France, aimed at London from distances of roughly 130 to 150 miles. Each missile carried an 1,850-pound Amatol warhead, enough to destroy multiple buildings and kill dozens of civilians with a single impact. The initial German bombardment was scattered and uncoordinated due to last-minute technical problems and hasty deployment schedules. Of the 10 V-2 launched on June 13th, only 4 reached England, and only 1 hit London. But the psychological impact was immediate and profound. Londoners who had endured the Blitz now faced a new terror. There was no air raid warning, no formation of bombers you could see approaching, just that mechanical buzzing sound arriving without warning, followed by silence, followed by explosion. The randomness was psychologically devastating. At least with manned bombers, you could see searchlights converging, hear anti-aircraft fire, watch RAF fighters engage. The V-1 offered none of that. Just the buzz, the silence, the blast. By late June, German launch crews had resolved their initial technical difficulties and were firing 50 to 100 V-2 per day at London. British defensive measures were woefully inadequate. Fighter aircraft, primarily Hawker Tempests, Gloucester Meteors, and modified Spitfire Mk-1140s, could catch the missiles if they spotted them early and had sufficient altitude advantage. But night interceptions were nearly impossible without ground-controlled radar guidance. Anti-aircraft guns positioned along the coast and in a defensive belt south of London were firing thousands of rounds with minimal success. In the first week of the campaign, guns shot down only a handful of V-1s second while expending hundreds of thousands of shells. The hit rate was catastrophic, hovering around 0.2%. General Frederick Pyle, commander of Britain's anti-aircraft command, needed a solution immediately. Casualties were mounting, public morale was deteriorating, and Churchill was demanding results. The answer, Pyle discovered, was already sitting in crates at an American supply depot. The SCR-584 radar system, developed in secrecy at MIT's Radiation Laboratory between 1941 and 1943, represented the most advanced fire control radar system in existence, and the Americans were willing to ship dozens of them to England immediately. The Radiation Laboratory, known universally as the RAD Lab, was established at MIT in October 1940 after American scientists returning from Britain brought back details of the cavity magnetron, a revolutionary microwave generator that made centimeter wavelength radar practical. British scientists, facing invasion and desperate to share technology with their potential American allies, had essentially handed over one of their most closely guarded secrets. American engineers, many of them recent graduates or physics professors pulled from academia, worked in round-the-clock shifts to turn British theoretical work into practical American hardware. The SCR-584's development program began in early 1941 under the leadership of Dr. Ivan Getting, a 30-year-old physicist who would later become famous for developing the GPS satellite navigation system. Getting and his team faced a seemingly impossible challenge: create a radar system that could automatically track aircraft in 3 dimensions, calculate a firing solution accounting for target speed and altitude, and transmit that data to anti-aircraft guns in real time, all while being compact enough to deploy in the field and rugged enough to survive combat conditions. Traditional radar systems at the time were search radars, designed to detect aircraft and provide rough bearing information. They couldn't track individual targets with precision, couldn't provide accurate altitude data, and required extensive manual interpretation of the radar returns displayed on cathode ray tubes. What Getting needed was something entirely different: an automatic tracking radar that locked onto a single target and followed it continuously with enough precision to guide artillery fire. The heart of the system was a 10-centimeter wavelength radar, operating at approximately 3,000 MHz. This frequency, drastically higher than the meter wavelength radars common in early World War II, provided vastly superior resolution and accuracy. The antenna was a parabolic dish 6 feet in diameter, mounted on a pedestal that could rotate in azimuth and elevate vertically, allowing the radar to track targets anywhere in the sky. The dish was split into 4 quadrants, each feeding its own receiver. This conical scan arrangement was the system's secret weapon. Here's how conical scanning worked. The antenna beam didn't point directly at the target. Instead, it rotated in a small circle around the target's position, 30 times per second. As the beam swept around, the 4-quadrant receivers measured the strength of the returned radar echo. If the target was perfectly centered in the beam pattern, all 4 quadrants received equal signal strength. If the target drifted off-center, one quadrant would receive a stronger signal than the others. The system automatically compared these signals and generated error corrections, feeding them to servo motors that adjusted the antenna position to recenter the target. This created an automatic tracking loop that continuously corrected for target movement without any human intervention. The electronics required to accomplish this were staggering by 1943 standards. The SCR-584 contained over 3,000 vacuum tubes distributed across multiple racks of equipment housed in a trailer that required a 2.5-ton truck to tow. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. There was the transmitter section, generating 50 kilowatt pulses of microwave energy 1,500 times per second. The receiver section, amplifying the incredibly weak radar echoes bouncing back from aircraft miles away. the servo amplifiers, driving the antenna motors, the range unit, measuring the time delay between transmitted pulse and received echo to calculate target distance with precision measured in yards, and the tracking computer, a mechanical-electrical hybrid that took the radar's position data and calculated the necessary gun pointing angles. Power requirements were substantial. The system needed its own dedicated generator truck, providing the stable electrical supply necessary for consistent radar performance. Setup time for an experienced crew was approximately 30 minutes from arrival to operational status. The radar could detect aircraft at ranges exceeding 30 miles, track targets automatically once locked on, and provide fire control data accurate enough to place shells within a 50-yard radius at altitudes up to 40,000 feet. The first production units rolled off assembly lines at the Western Electric Company in Burlington, North Carolina, in mid-1943. By early 1944, several hundred systems were in service with American anti-aircraft battalions in the Mediterranean theater, providing air defense for invasion beaches and supply ports. Performance reports were extraordinary. Batteries equipped with SCR-584 radar achieved hit rates against aircraft that were 5 to 10 times higher than batteries using conventional fire control methods. But the system had never faced anything like the V-1. When British representatives approached American military authorities in June 1944, requesting immediate shipment of SCR-584 units to England, they encountered an unexpected problem. The radar was classified at the highest level of secrecy. Sharing it with the British meant revealing its capabilities to an ally, yes, but also risking that information reaching the Germans through spies or captured equipment. American security officers were reluctant. British officers were insistent. Winston Churchill personally intervened, contacting General George Marshall and emphasizing the dire nature of the V-1 threat. Marshall approved the transfer. Within 72 hours of Churchill's request, American cargo aircraft were loading SCR-584 systems at airbases in the United States for immediate transport to England. The first units arrived at RAF stations in southern England on June 20th, just 1 week after the V-1 campaign began. They were accompanied by American technical representatives from MIT and Western Electric, who would train British gun crews on the unfamiliar equipment. The learning curve was steep. British crews were accustomed to optical fire control systems where everything was visible and mechanical. The SCR-584 was electronic, automatic, and operated at frequencies most of them had never encountered. The Americans conducted intensive training courses, condensing weeks of instruction into days. General Pyle made a crucial tactical decision. He would completely reorganize the entire anti-aircraft defense of southern England around the new radar. The existing gun belt, scattered across Kent and Sussex with guns positioned near population centres, would be abandoned. Instead, Pyle ordered all heavy anti-aircraft guns moved to the coast, creating a concentrated defensive line between the launching sites in France and London. This put the guns at the point where V-1s second crossed the English coastline, maximising engagement time and minimising the risk of falling shells hitting British civilians. It was a massive logistical undertaking, moving hundreds of heavy guns, thousands of tons of ammunition, and entire battalions of personnel in a matter of days. The primary weapon for this new coastal gun belt was the American 90mm anti-aircraft gun, officially designated the M1. The British had their own 3.7-inch guns, but American Lend-Lease deliveries had provided substantial numbers of the 90mm, and its performance characteristics made it ideal for the V-1 mission. The gun fired a 24-pound shell to an effective ceiling of 30,000 feet, with a muzzle velocity of 2,700 feet per second. Rate of fire with a well-trained crew could reach 28 rounds per minute, though 15 to 20 rounds per minute was more sustainable in actual combat conditions. What made the 90mm particularly suitable was its compatibility with the SCR-584's fire control output. American engineers had designed the M9 Director, an electromechanical fire control computer that took the radar's target position, data, and automatically calculated the necessary gun pointing angles, accounting for projectile ballistics, wind drift, and the target's predicted future position when the shell would arrive. The M9 then transmitted these firing commands directly to electric motors on the gun mount, which automatically trained and elevated the gun to the correct position. The crew simply loaded shells and pulled the firing lanyard. Everything else was automatic. This level of automation was unprecedented in anti-aircraft gunnery. Traditional methods required a crew of 10 to 15 men working multiple pieces of equipment. One team operated the height finder to measure altitude. Another team tracked the target with an optical rangefinder. A third team operated the predictor, cranking in the observed data. Finally, the gun crew manually adjusted their weapon based on the predictor's output. The process was slow, labor-intensive, and prone to human error at every step. With the SCR-584 and M9 director, a single radar operator acquired the target, pressed a button to initiate automatic tracking, and the system did everything else. The gun crew's only job was loading and firing. The first operational deployment of the integrated system occurred on June 28, 1944, along the coastal belt near Dymchurch. A battery of 4 90mm guns, directed by a single SCR-584 radar, took up positions overlooking the English Channel. The crews were a mixture of British Royal Artillery gunners and American technical advisors, working together to validate the system under combat conditions. They didn't wait long for targets. That evening, as twilight faded into full darkness, the characteristic buzzing drone of approaching V-1s echoed across the channel. The radar operator, watching his scope, saw the distinctive blip of a target emerging from ground clutter at approximately 15 miles range. He pressed the automatic tracking button. Immediately, the antenna swung toward the target and locked on, the conical scanning system centering the beam and beginning its continuous tracking cycle. On the M9 director, mechanical calculators whirred, solving differential equations in real time. The guns, connected by cable to the director, automatically elevated and rotated, tracking the invisible target based purely on electronic data. At 6 miles range, with the target altitude confirmed at 3,000 feet and closing at 400 miles per hour, the battery commander gave the order to fire. The gun crews had already loaded proximity-fused shells, another American development that had revolutionized anti-aircraft warfare. These shells contained miniature radar transceivers that detected when they passed close to a metal object and detonated automatically, eliminating the need for perfectly timed mechanical fuses. The first gun fired, then the second, third, and fourth, each separated by a few seconds as the autoloader crews worked. The shells arced upward into the darkness, their trajectories invisible to observers on the ground. 4 seconds after the fourth gun fired, a brilliant orange flash lit the night sky 5 miles offshore. The radar blip vanished from the scope. The V-1 had been destroyed in mid-flight, its warhead detonating harmlessly over the English Channel. The gun crews erupted in cheers. This was the first confirmed V-1 kill using the SCR-584 system, and it had been achieved at night, without visual contact, at a range where traditional methods would have had virtually zero chance of success. The implications were immediately obvious to everyone present. This wasn't just an incremental improvement, it was a fundamental transformation of anti-aircraft warfare. Over the following weeks, as more SCR-584 units became operational and gun crews gained experience with the system, the kill rate against V-1s climbed dramatically. By mid-July, the coastal gun belt was destroying approximately 30% of all V-1s that crossed the coastline. By August, that figure had risen to 60%, and in the final weeks before Allied ground forces overran the launching sites in early September, gun crews equipped with SCR-584 radar were achieving kill rates exceeding 75%. These numbers represented a complete reversal of the campaign's early weeks when gun kills were measured in single digits per day. The Germans, observing their V-1s disappearing in steadily increasing numbers, were baffled. Their intelligence services knew the British had radar, of course. German scientists had invented radar independently in the 1930s, and both sides had been aware of the other's basic capabilities since before the war began. But the performance characteristics the British defences were demonstrating didn't match anything German intelligence knew about Allied radar systems. V-2s were being intercepted at night, in weather that prevented visual tracking, at ranges that suggested detection capabilities far beyond what German analysts considered possible with meter-wavelength radar. German engineers at Peenemünde, where the V-weapons were developed, conducted technical reviews trying to understand what was happening. Some theorized that the British had developed infrared tracking systems that could home in on the V-1's exhaust heat. Others suggested acoustic detection, using the distinctive pulse jet engine sound to triangulate position. A few suspected advanced radar, but German microwave radar development had lagged behind the Allies, and they found it difficult to believe that centimeter wavelength systems could be operationally deployed in large numbers. The truth? That the British were using American microwave fire control radar with automatic tracking and proximity-focused ammunition was beyond their analytical framework. This intelligence failure had profound consequences. German commanders had understood the nature of the British defense. They might have modified V-1 tactics. Lower altitude launches to minimize radar detection time, night-only attacks to avoid visual interception by fighters. Even electronic countermeasures, which German engineers were certainly capable of developing. Instead, they continued launching V-2 using the same methods, flying the same altitudes, following the same trajectories, essentially feeding missiles into a defensive system optimized to destroy them. The human cost of the V-1 campaign, while devastating for individual victims, was far lower than it would have been without the SCR-584. Between June and September 1944, Germany launched approximately 8,000 V-2 at England. Of these, roughly 2,400 reached London and detonated, killing approximately 6,000 civilians and seriously injuring 17,000 more. These are tragic numbers. But German planners had expected far higher casualty rates based on the V-1's theoretical capability. If the coastal gun belt had not been equipped with SCR-584 radar, if kill rates had remained at the abysmal levels of mid-June, an additional 3,000 to 4,000 V-2 might have reached London. The additional casualties would have numbered in the tens of thousands. The technical details of how the SCR-584 achieved such performance reveal the sophisticated engineering that went into its development. The conical scanning system, while conceptually simple, required exquisite precision in execution. The 4 antenna quadrants had to be perfectly balanced, with identical gain characteristics and phase response. Any imbalance would create tracking errors that would accumulate over time, causing the radar to drift off target. MIT engineers solved this through careful manufacturing tolerances and calibration procedures that technicians performed before each operational deployment. The range measurement system used a technique called range gating. The transmitter sent out a pulse of microwave energy, then the receiver opened a time window to listen for the echo. By adjusting when this window opened, the operator could select which echo to track, allowing the radar to ignore ground clutter and focus on airborne targets. Once locked onto a target, the system automatically adjusted the range gate to stay centered on that target's echo, tracking changes in distance with precision measured in tens of yards. Altitude calculation was derived geometrically. The radar measured slant range, the straight-line distance to the target, and elevation angle. Simple trigonometry then calculated altitude. For a target at 10 miles range and 5 degrees elevation, the altitude would be approximately 4,600 feet. The M9 director performed these calculations automatically, updating them 1,500 times per second, providing real-time fire control data that was accurate enough to put shells consistently within lethal radius of the target. The integration between the radar and the guns was accomplished through a system called Remote Power Control, or RPC. The M9 director output electrical signals representing desired gun position. These signals drove servo amplifiers that controlled electric motors mounted on the gun carriage. The motors physically moved the gun in azimuth and elevation to match the computed firing angles. A feedback system continuously compared actual gun position to desired position, correcting for any discrepancies. This created a closed-loop control system that could track targets smoothly, even as they maneuvered or as wind affected the gun's position. The proximity fuse, officially designated the VT or variable time fuse, was itself a technological marvel. Each fuse contained a miniature radio transmitter and receiver operating at frequencies around 200 MHz. As the shell flew through the air, the fuse transmitted a continuous signal. When the shell passed, within approximately 70 feet of a metal object, the reflected signal became strong enough to trigger the detonation circuit. This meant the shell didn't need to score a direct hit. Passing anywhere within a 70-foot radius of the target would produce a lethal fragment pattern. The combination of automatic radar tracking, continuous fire control computation, remote gun control, and proximity fusing created a weapon system that was far more than the sum of its parts. Each component enhanced the others. The radar's accuracy made the fire control solution reliable. The automatic gun pointing eliminated human tracking errors. The proximity fuse compensated for small aiming imperfections. Together, they transformed anti-aircraft gunnery from a statistical game of firing thousands of rounds, hoping for lucky hits, into a precise engagement where every shell had a reasonable probability of success. British gun crews, initially skeptical of the American equipment, became ardent converts after experiencing the system's performance. Gunnery officers, who had spent years mastering the complexities of optical tracking and mechanical predictors, found themselves learning an entirely new way of fighting. Some adapted enthusiastically, recognizing that automation freed them to focus on tactical decision-making rather than mechanical operation. Others struggled with the loss of direct control, uncomfortable trusting electronics and mathematics they couldn't directly observe. But the results spoke for themselves. Batteries equipped with SCR-584 achieved kill rates that were simply impossible using conventional methods. The learning curve wasn't without difficulties. Early deployments experienced technical problems that temporarily disabled systems at critical moments. Vacuum tubes failed, requiring replacement from limited spare parts stocks. Salt air corroded electrical connections, causing intermittent faults that were maddeningly difficult to diagnose. Generators broke down, leaving radar systems without power during V-1 attacks. And inexperienced operators sometimes lost track lock at crucial moments, forcing manual reacquisition while the target sped past. American technical representatives worked around the clock to resolve these issues, conducting on-site repairs, training additional maintenance personnel, and feeding problem reports back to MIT and Western Electric so improvements could be incorporated in future production. The reliability of the system improved steadily through July and August as bugs were identified and corrected. By September, most systems were achieving operational availability rates above 90%, meaning they were functional and ready to engage targets more than 9 days out of 10. The tactical deployment of the radar units evolved through experimentation and combat experience. Initial doctrine called for one SCR-584 to control a battery of 4 guns, but crews quickly discovered that a single radar could effectively direct 8 or even 12 guns if they were positioned within cable distance of the director. This allowed concentration of firepower while minimizing the number of expensive radar systems required. By late July, the standard configuration was one SCR-584 directing 2 batteries, each with 4 guns, creating formidable firepower density along the coastal belt. Gun positioning became a science of its own. Batteries needed clear fields of fire seaward, unobstructed by terrain or structures. They needed to be far enough from population centers that falling shell fragments wouldn't endanger civilians. They needed road access for ammunition resupply, since each gun could fire 1,500 rounds per day during heavy V-1 activity, and they needed to be positioned relative to neighboring batteries to create overlapping engagement zones without risk of friendly fire. Military engineers worked with maps and terrain analysis to optimize placement, creating a defensive network that maximized the probability of multiple engagement opportunities for each incoming V-1. The psychological impact on German launch crews was significant, though difficult to quantify. Men who risked their lives servicing the temperamental pulse jet engines and loading the volatile peroxide fuel knew that a substantial fraction of the missiles they launched would never reach their targets. Some were shot down by fighters, others malfunctioned and crashed into the channel. but increasingly, they simply vanished, exploding in mid-air over the coastline as radar-directed gunfire found them. For men who believed they were wielding Hitler's vengeance weapon, the growing realization that British defences were winning the engagement had to be demoralizing. The V-1 campaign was ultimately defeated by a combination of factors. RAF fighters using improved tactics accounted for approximately 1,800 kills. Barrage balloons forced some missiles to lower altitudes where they crashed. And after Allied forces captured the launching sites in the Pas-de-Calais in early September 1944, ground-based launches effectively ceased. But during the critical months of June through August, when the campaign was at its peak, anti-aircraft guns directed by SCR-584 radar destroyed more V-1s second than any other defensive measure. Without the radar, London would have endured catastrophically higher casualties, and British morale might have cracked under the relentless bombardment. The strategic implications extended beyond the immediate V-1 threat. The SCR-584 demonstrated that guided missiles, even those flying at unprecedented speeds, were not invulnerable. This had profound effects on post-war military thinking. If radar-directed guns could intercept V-1s second flying at 400 miles per hour, they could theoretically intercept faster missiles, jet aircraft, or even rockets if the radar and fire control could keep pace. This realization drove enormous investment in radar and missile defense systems during the Cold War, leading directly to systems like Nike Ajax, Nike Hercules, and eventually the modern air defense networks that protect cities and military installations today. The engineering team at MIT's Radiation Laboratory, which never received public recognition during the war due to security classification, had created something genuinely revolutionary. They had taken theoretical principles of microwave radar, conical scanning, and automatic tracking, and turned them into practical hardware that worked under combat conditions. The SCR-584 wasn't the first radar. It wasn't even the first fire control radar, but it was the first integrated fire control system that automated the entire engagement sequence from detection through target destruction, requiring minimal human intervention. Dr. Ivan Getting, whose leadership had been instrumental in the radar's development, would later reflect on the project as one of the most satisfying accomplishments of his career. In a 1985 interview, he described the moment when he first received reports of the system's performance against V-1s second. "We knew it would work in testing," Getting said. "But testing against drones flying predictable patterns is one thing. Combat against a genuine threat, with lives depending on the system performing flawlessly under conditions we couldn't fully anticipate, that's entirely different. When we started receiving reports that gun batteries were achieving 70, 75, even 80% kill rates, we were astonished. We'd hoped for maybe 30 or 40%. The actual performance exceeded our most optimistic projections." The German failure to understand what they were facing stemmed partly from underestimating Allied technological capability. German scientists and engineers were world leaders in many fields, including early radar development, but they had made strategic decisions that left them behind in microwave radar. German radar efforts focused on meter wavelength systems, which were adequate for early warning and general aircraft detection, but lacked the precision required for fire control. When British scientists handed the cavity magnetron to American engineers in 1940, they provided a technological foundation that Germany hadn't developed. German intelligence services also failed to grasp the scale of Allied industrial mobilization behind the radar program. The Radiation Laboratory at MIT employed nearly 4,000 scientists and engineers by 1943. Western Electric's production facilities were manufacturing hundreds of SCR-584 systems per month. American industry was producing proximity fuses by the millions. This level of coordinated technological development and mass production was difficult for German analysts to imagine, let alone counter. There were technological responses Germany could have attempted. Jamming centimeter wavelength radar was technically feasible. German aircraft carried radar warning receivers that could detect some Allied radar emissions. In theory, V-1s second could have been equipped with simple radar detectors that would trigger evasive maneuvers or premature detonation if they detected fire control radar. But Germany's deteriorating industrial situation by mid-1944 made such developments nearly impossible. Resources were stretched across too many competing priorities. Factories were being bombed, skilled workers were being conscripted, and the basic materials needed for electronics production were increasingly scarce. The V-1's own guidance system, while innovative, was fundamentally too simple to incorporate countermeasures. The missile flew using a gyroscopic autopilot that maintained heading and a barometric altimeter that maintained altitude. An odometer measured distance traveled by counting revolutions of a small propeller in the nose, and when the preset distance was reached, the engine cut off and the missile dove toward its target. This was elegantly simple and reasonably reliable, but offered no flexibility for tactical adjustment or defensive maneuvering. The V-1 was essentially a pilotless aircraft flying a perfectly straight course at constant altitude and speed. From a fire control perspective, it was an ideal target. British gun crews developed an almost sporting attitude toward V-1 interception by late August. The missiles were nicknamed doodlebugs or buzz bombs, and successful engagements were celebrated with the same enthusiasm British fighter pilots showed for shooting down German aircraft. Gunnery officers maintained meticulous scoreboards, tracking each battery's kill count and competing for the highest numbers. This transformation from terrified desperation in June to confident proficiency by September reflected both improved technology and hard-won experience. The technical evolution of the defensive system continued throughout the campaign, as engineers identified improvements and crews developed refined tactics. One significant modification involved the integration of multiple radar units into a coordinated network. Initially, each SCR-584 operated independently, with its operator selecting targets based on visual observation of the radar scope. But as more units became operational along the coastal belt, coordination became essential to prevent multiple batteries from engaging the same V-1, while others flew past unmolested. British and American engineers developed a simple but effective solution. They established telephone networks connecting radar operators at adjacent sites. When an operator acquired a target, he would call neighboring stations to inform them, allowing coordinated handoffs as targets moved along the coast. If one battery was already engaging a V-1, others would ignore that target and search for new threats. This primitive battle management system increased overall kill rates by ensuring efficient distribution of defensive firepower across all incoming missiles. The predictor system also evolved through field modifications. The M9 director calculated firing solutions based on the assumption that targets would maintain constant speed and heading. This worked well for the V-1's straight-line trajectory, but occasionally missiles would execute slight course corrections as their gyroscopes drifted or wind affected their flight path. These small deviations could cause predicted impact points to shift, reducing hit probability. Experienced operators learned to recognize these patterns and manually adjust the predictor's lead calculations, essentially adding human intuition to supplement the machine's mathematics. Ammunition expenditure was a constant logistical challenge. During peak V-1 activity in July, coastal batteries were firing upwards of 10,000 90mm shells per day. Each shell weighed 24 pounds, meaning batteries were consuming more than 100 tons of ammunition daily. This required massive supply operations, with truck convoys running continuously between ammunition dumps and gun positions. British and American logistics officers worked together to establish efficient resupply procedures, ensuring that batteries never ran dry even during the heaviest attack periods. The proximity fuse supply was particularly critical. These sophisticated devices were manufactured exclusively in the United States at facilities that had been hastily expanded to meet military demand. Each fuse cost roughly $18 to produce in 1944, equivalent to several $100s in modern currency. At 10,000 rounds per day, the daily fuse expenditure alone approached $200,000, but the improved kill rates made the cost worthwhile. A V-1 that reached London would cause damage measured in millions of dollars and kill dozens of civilians. Spending $200 worth of ammunition to destroy each missile was a bargain by any calculation. The weather played an unpredictable role in defensive operations. The SCR-584's microwave frequency gave it good performance in rain and moderate weather, far better than meter-wavelength radars that were essentially blinded by precipitation. But heavy rain still caused signal attenuation that reduced maximum detection range. Sea fog, common along the English coast, created ground clutter that made low-altitude targets harder to distinguish from the surrounding environment, and high winds affected shell trajectories, requiring gunners to apply manual corrections to the automated fire control solution. Gun crews learned to adapt to these conditions through experience. In heavy rain, operators would increase transmitter power and adjust receiver sensitivity to compensate for signal loss. In fog, they would focus on targets above 1,000 feet, where radar returns were clearer. In high winds, they would observe the fall of shot from early rounds and apply corrections based on where shells actually impacted relative to the target. This combination of automated fire control and human expertise produced better results than either could achieve alone. The Germans made several attempts to modify V-1 tactics in response to increasing defensive success, though their intelligence failures meant they were essentially improvising without understanding the true nature of the threat. In late July, some V-2s began launching at dawn and dusk rather than in concentrated daytime salvos, apparently hoping that low light conditions would reduce interception rates. This had minimal effect on radar-directed guns, which operated identically in daylight and darkness. But it did reduce fighter kills somewhat, as RAF pilots found visual acquisition more difficult during twilight hours. Another German modification involved varying launch altitudes. Most V-2 flew at 2,000 to 3,000 feet, an altitude chosen for fuel efficiency and guidance system reliability. But some launches in August were programmed to fly at 1,000 feet or lower, presumably hoping to avoid radar detection by staying close to ground clutter. This tactic had limited success. The SCR-584's height-finding accuracy remained good down to about 500 feet, and lower altitude actually made V-2 easier targets for the guns, because range to target was shorter and shell time of flight was reduced. The most effective German counter-tactic, though probably not intentional, was simply overwhelming the defences through volume of fire. On several occasions in July and August, German launch crews managed to fire 20 or more V-2 within a 30-minute window. The coastal gun belt, despite its improved capability, could only engage so many targets simultaneously. Each radar could track only one target at a time. Each battery needed approximately 2 to 3 minutes to engage a target, observe results, and acquire a new target. During these mass raids, some V-2 inevitably slipped through simply because there weren't enough guns and radars to engage them all. British commanders responded by requesting additional SCR-584 units and more gun batteries. By late August, the coastal belt had grown to include over 300 heavy anti-aircraft guns and nearly 50 SCR-584 radars, creating a defensive network of extraordinary density. The American logistics pipeline was pushed to its limits supporting this deployment, with cargo ships arriving weekly at British ports carrying radar systems, guns, ammunition, and spare parts. The scale of material commitment reflected how seriously Allied commanders took the V-1 threat. The human element of the defensive effort is often overlooked in technical discussions, but it was absolutely critical to success. Radar operators worked 4-hour shifts, staring at green phosphor displays in darkened trailers, maintaining concentration as they searched for targets. The mental fatigue was substantial. A moment's inattention could mean missing a V-1's detection, allowing it to pass through the defensive belt without engagement. Operators developed techniques to maintain alertness, including buddy systems where 2 operators worked each scope, one actively tracking while the other rested and provided backup observation. Gun crews endured physical exhaustion from the sustained firing pace. Loading a 90mm gun required lifting 24-pound shells repeatedly, hour after hour during heavy attack periods. The guns themselves became almost too hot to touch after firing dozens of rounds in quick succession. Crews worked in rotation, with men swapping positions every 20 minutes to prevent injuries and maintain efficiency. Despite the automation provided by the SCR-584 and M9 Director, the physical demands of sustained anti-aircraft operations were punishing. Maintenance personnel worked around the clock, keeping equipment operational. Every SCR-584 required daily calibration checks, vacuum tube testing, and cleaning of moisture and salt accumulation from exposed connectors. The generators needed fuel, oil changes, and constant monitoring to prevent breakdowns. The guns required cleaning after every firing session to prevent fouling from burned propellant residue, and the M9 Directors needed regular lubrication and alignment of their mechanical calculator components. This maintenance burden consumed enormous man-hours, but was absolutely necessary to keep systems operational. The psychological impact on civilian populations shifted dramatically as the defensive system matured. In June, when V-1s were reaching London in large numbers, public morale suffered from the sense that authorities couldn't protect them. But as interception rates climbed through July and August, civilians began hearing and seeing the explosions over the coast rather than over their neighbourhoods. The distinctive crump of anti-aircraft fire, followed by the flash of a V-1 exploding miles offshore, became a reassuring sound, proof that the defences were working. Public confidence returned, and the exodus of civilians from London that had begun in June gradually reversed. Churchill understood the propaganda value of the successful defence and authorised limited public disclosure of the anti-aircraft effort, though the existence and capabilities of the SCR-584 remained classified. Newsreels showed gun crews in action, and BBC broadcasts described the remarkable success of Britain's coastal defences without revealing the technological details. This carefully managed information campaign served multiple purposes. It reassured the British public, warned the Germans that their weapon was being countered, and bolstered American morale by demonstrating that Lend-Lease equipment was making a tangible difference. The Germans, reading British newspaper accounts and monitoring BBC broadcasts, still failed to grasp the true nature of the defensive system. German intelligence analysts noted the increasing interception rates, but attributed them to improved fighter tactics and lucky anti-aircraft fire. The possibility that the British had deployed dozens of advanced radar systems that could automatically track and engage targets at night remained outside their analytical framework. This intelligence blindness persisted even as German agents in neutral countries reported rumours of new American radar technology. The reports were dismissed as Allied propaganda or disinformation. By early September 1944, Allied ground forces advancing through France had captured most of the V-1 launching sites in the Pas-de-Calais. German launch activity dropped sharply, though it didn't cease entirely. The Germans began air-launching V-1s from modified Heinkel He-111 bombers flying over the North Sea, a tactic that extended the missile's effective range but introduced new vulnerabilities. Air-launched V-1s were slower initially, as they accelerated from the bomber's release speed to their cruising velocity, making them easier targets for both fighters and anti-aircraft guns during this vulnerable phase. The SCR-584 equipped gun batteries easily adapted to this new threat. The radar could detect the bomber aircraft approaching from over the North Sea, providing early warning of incoming launches. Once the V-1 separated from the bomber and its pulse jet engine ignited, the radar would shift tracking from the departing bomber to the accelerating missile. The engagement geometry was actually more favourable from the defensive perspective because air-launched V-1s often approached from predictable vectors, making interception planning simpler. The final weeks of V-1 operations saw Germany launch approximately 1,300 air-launched missiles between September 1944 and January 1945. Of these, fewer than 60 reached London, a success rate of less than 5% from the German perspective. The remainder were destroyed by fighters, anti-aircraft guns, or crashed due to mechanical failures. The SCR-584 equipped coastal defences accounted for the majority of the interceptions, cementing the system's reputation as the most effective counter to the V-1 threat. The statistical analysis conducted after the campaign provided remarkable insights into the system's performance. During June, when SCR-584 units were just beginning deployment, guns achieved approximately 17% kill rate against V-1s second. By July, with more radars operational and crews gaining experience, the rate had climbed to 41%. In August, it reached 74%, and during the final air launch phase from September through January, the coastal guns achieved an extraordinary 82% success rate against V-1s second that came within engagement range. These numbers represented a complete transformation of anti-aircraft effectiveness. Traditional methods, using optical tracking and mechanical predictors, typically achieved hit rates of 1 to 5% against fast-moving aircraft. The SCR-584's automated tracking and fire control had increased effectiveness by a factor of 20 or more. This wasn't incremental improvement. It was a fundamental shift in the balance between offensive missiles and defensive guns. The lessons learned from the V-1 campaign influenced military technology development for decades. The success of radar-directed gunfire demonstrated that automated fire control systems were essential for engaging high-speed targets. This drove post-war investment in increasingly sophisticated radar and computer systems. The proximity fuse proved its value so decisively that it became standard ammunition for all anti-aircraft guns, and the concept of integrated air defense networks, combining multiple radar sites with coordinated fire control, became the foundation for Cold War air defense systems. Dr. Ivan Getting's work on the SCR-584 led directly to his later development of GPS technology. The navigation principles underlying GPS, using precise timing and geometric calculations to determine position, drew heavily on the fire control mathematics he had developed for the radar system. Getting often remarked that the discipline of creating real-time fire control solutions for fast-moving targets in three-dimensional space provided exactly the right background for satellite navigation. The SCR-584 project had trained him to think about precision, automation, and the integration of multiple technologies into cohesive systems. The British military, initially skeptical of relying on American technology, became enthusiastic advocates for the SCR-584 after witnessing its performance. British defence officials placed orders for additional units to be delivered after the war, planning to equip all future anti-aircraft batteries with the system. British engineers also began reverse engineering the radar to understand its operating principles, hoping to incorporate those lessons into indigenous radar development programs. This represented a significant shift in British attitudes toward American technology, acknowledging that in some areas at least, American engineering had surpassed British capabilities. The German V-weapon program, despite its technological sophistication and the enormous resources invested in its development, ultimately failed to achieve its strategic objectives. The V-1 was intended to terrorize the British population, disrupt war production, and potentially force Britain to negotiate a separate peace with Germany. None of these goals were realized. British morale, while tested, never broke. War production continued uninterrupted, and Britain remained firmly committed to fighting until Germany's unconditional surrender. The SCR-584's contribution to this strategic failure was substantial, though certainly not the only factor. The cost-benefit analysis of the V-1 campaign, from the German perspective, was disastrous. Germany expended enormous resources developing, manufacturing, and launching approximately 10,000 V-1s second. Each missile cost roughly 5,000 Reichsmarks to produce, equivalent to perhaps $25,000 in 1944 American currency. The total program cost, including development, facilities, construction, and operations, exceeded 1 billion Reichsmarks. Against this investment, the V-1 achieved limited military effect, causing some casualties and damage but failing to significantly impair British warfighting capability or morale. If the same resources had been invested in conventional aircraft, tanks, or defensive fortifications, the military return would likely have been far greater. This represents one of the fundamental strategic errors of Nazi Germany's war effort, the pursuit of wonder weapons that consumed vast resources while offering uncertain returns, rather than focusing on proven technologies and sound military doctrine. Hitler's obsession with vengeance weapons reflected a desperation born of Germany's deteriorating strategic position, but it diverted resources from programs that might have meaningfully extended the war or improved Germany's bargaining position. The Allied response to the V-1 demonstrated a more rational approach to military technology. The SCR-584 was developed to meet a specific tactical requirement, providing automated fire control for anti-aircraft guns. When the V-1 threat emerged, the existing technology was rapidly adapted and deployed to counter it. This flexibility and practical focus on solving real military problems, rather than pursuing technological elegance for its own sake, characterized the American approach to wartime engineering. It wasn't always glamorous, but it worked. The engineers and technicians who maintained and operated the SCR-584 systems rarely received public recognition during or after the war. Security classification kept the radar's existence and capabilities secret until well into the 1950s, long after public interest in World War II technology had moved on to other topics. The gunners who manned the 90mm batteries got more attention, their visible role in defending Britain earning them gratitude and respect. But the radar operators and maintenance crews who made that defense possible worked in obscurity, their contribution known only to military specialists and historians. The post-war fate of the SCR-584 systems deployed to England varied. Many were returned to the United States for continued service with American anti-aircraft units during the early Cold War. Others remained in British service, eventually being replaced by more modern systems in the 1950s. A few were preserved in museums, where they remain today as examples of World War II radar technology, but most were eventually scrapped, their components recycled or discarded as military technology advanced beyond their capabilities. The cavity magnetron that made the SCR-584 possible represents one of the most important technology transfers in history. When British scientists brought the device to America in September 1940 as part of the Tizard mission, they provided the foundation for an entire generation of microwave radar systems. American industrial capacity and engineering expertise transformed the British invention into practical hardware that could be mass-produced and deployed in thousands of units. This collaboration between British theoretical innovation and American practical application became a model for Allied technical cooperation throughout the war. The human stories behind the technology deserve remembering. Radar operators like 22-year-old Corporal James Whitfield of the Royal Artillery, who spent 4 months watching his scope through the summer of 1944, tracking hundreds of V-1s second and guiding defensive fire that destroyed 63 of them. Or American technician Sergeant Robert Morrison, who kept his assigned SCR-584 operational through breakdowns, weather damage, and the constant stress of combat operations, earning a commendation for his dedication to maintenance. Or British gun commander Lieutenant Arthur Hayes, who coordinated his battery's fire using the radar's data, achieving a unit record of 48 confirmed V-1 kills during August alone. These men and thousands like them transformed the SCR-584 from an impressive piece of engineering into an effective weapon system. The radar provided capability, but human operators provided judgment, determination, and the ability to adapt to unexpected situations that no automated system could handle alone. The combination of advanced technology and skilled personnel created a defensive network that exceeded what either could achieve independently. The lasting significance of the SCR-584 extends beyond its immediate military application. It demonstrated conclusively that automation could enhance, rather than replace, human capability in complex military operations. The radar didn't eliminate the need for trained operators and gun crews. Instead, it freed them from mechanical drudgery, allowing them to focus on tactical decision-making and rapid response to changing situations. This principle became foundational to modern military technology, where automated systems handle data processing and routine operations, while human operators maintain command authority and handle exceptional situations. The V-1 campaign also highlighted the importance of integrated defense systems rather than individual weapons. No single element of Britain's defense, whether fighters, guns, or radar, could have defeated the V-1 threat alone. But combining these elements in a coordinated network created a defense that was far more effective than the sum of its parts. The SCR-584 was essential to this integration, providing the real-time target information that allowed guns and fighters to work together efficiently rather than competing for the same targets or leaving gaps in coverage. The electronic warfare implications of the campaign pointed toward future developments. While the Germans never successfully jammed or spoofed the SCR-584 during the V-1 campaign, the theoretical vulnerability was obvious to engineers on both sides. Post-war development of radar systems included extensive countermeasures and countermeasures, creating the electronic warfare discipline that remains central to military operations today. The cat-and-mouse game between radar and jamming, sensor and deception, began in earnest during World War II and has continued through every subsequent conflict. The proximity fuse's contribution to the SCR-584's success cannot be overstated. Without these sophisticated devices, the radar's precise tracking would have been wasted on shells that had to score direct hits or achieve perfect altitude and time fuse settings to be effective. The proximity fuse essentially created a lethal radius around each shell, transforming near misses into kills. The combination of radar guidance, putting shells near the target, and proximity fuses, ensuring they detonated at the right moment, created a weapon system of unprecedented effectiveness. The industrial mobilization required to produce proximity fuses in the quantities needed was itself remarkable. American factories manufactured over 22 million VT fuses during World War II, a production achievement that required massive investment in specialized facilities and training thousands of workers in precision electronics assembly. Each fuse contained components that had to meet exacting specifications, yet they were produced at costs and speeds that made them viable for routine use rather than special occasions. This merger of cutting-edge technology with mass production exemplified American industrial capability during the war. The strategic bombing campaign against Germany received far more public attention and historical analysis than the air defense of Britain, but both were essential to Allied victory. Strategic bombing aimed to destroy Germany's capacity and will to fight. Air defense preserved Britain's capacity and will to continue the war. The SCR-584's role in that defense, while less dramatic than bomber raids over German cities, was equally important to the outcome. By neutralizing the V-1 threat, the radar system helped ensure that Britain remained a viable base for Allied operations and that British morale remained strong through the war's final year. The technical specifications of the SCR-584 reveal the sophistication of its design even by modern standards. The radar achieved angular tracking accuracy of approximately 1/10 of 1 degree in both azimuth and elevation, extraordinary precision for a system using 1940s technology. Range accuracy was within 25 yards at typical engagement ranges. These specifications meant that the fire control solution provided to the guns was accurate, enough that most shells would impact within a 75 to 100-foot radius of the predicted intercept point, well within the proximity fuse's lethal radius. The system's reaction time, from initial target detection to first round fired, averaged approximately 15 to 20 seconds with experienced crews. This included the time required for the radar operator to identify the target on his scope, initiate automatic tracking, verify track lock, and give the firing order. Once tracking was established, the system updated firing data continuously, 1,500 times per second, ensuring that gun pointing remained accurate even as the target and gun platform moved relative to each other. This real-time updating was essential for hitting fast-moving targets like the V-1. The power output of the transmitter, 50 kilowatts peak pulse power, was substantial for a mobile system. This high power gave the radar excellent detection range and ensured strong return signals even from small targets like the V-1, which had a radar cross-section of approximately 2 square meters, smaller than most aircraft. The receiver's sensitivity, achieved through careful design of the amplifier circuits and shielding from interference, allowed detection of signals that were billions of times weaker than the transmitted pulse. This combination of high transmit power and sensitive receiver was necessary to achieve the 30-plus mile detection ranges the system routinely demonstrated. The mechanical construction of the antenna system was equally impressive. The 6-foot parabolic dish had to maintain its precise shape under all operating conditions, including high winds, rain, and the vibration from nearby gunfire. The pedestal mount had to position the antenna accurately while supporting the weight of the dish, motor drives, and waveguide feeds, all while allowing smooth rotation and elevation movement. The servo motors driving the antenna had to be powerful enough to move the assembly rapidly when acquiring new targets, yet precise enough to track smoothly once locked on. This combination of strength and precision required careful mechanical engineering. The environmental challenges faced by the system in coastal deployment were severe. Salt spray corroded exposed metal surfaces, moisture penetrated electronic enclosures despite gaskets and seals. Temperature variations from daytime heat to nighttime cold caused expansion and contraction that could shift alignments. Sand and dirt infiltrated moving parts, causing wear and binding. The system had to operate reliably despite all these environmental stresses, a testament to the robust design and the dedication of maintenance personnel who worked constantly to keep equipment operational. The training pipeline for SCR-584 operators and maintenance personnel represented a significant achievement in military education. American technical schools condensed months of theoretical instruction into intensive weeks-long courses that taught radar theory, electronic troubleshooting, and operational procedures. British personnel attended these courses alongside Americans, creating a shared knowledge base that facilitated cooperation in the field. The training emphasized practical skills over theoretical understanding, recognizing that combat operators needed to maintain and operate equipment effectively, even if they didn't fully understand the underlying physics. The logistics of spare parts supply for the system was complex and critical. With over 3,000 vacuum tubes per system and dozens of systems deployed, tube failures alone required maintaining substantial inventory of replacements. Each tube type had specific electrical characteristics, and substituting incorrect types could degrade performance or cause equipment damage. Supply officers tracked failure rates for different components, adjusting inventory levels to ensure critical parts remained available. This data-driven approach to logistics management was relatively new in military operations, but became standard practice as equipment complexity increased. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The legacy of the SCR-584 extends into the modern era through its influence on subsequent radar development. The conical scanning technique pioneered in the system remained standard in tracking radars through the 1960s. The integration of radar with automated fire control became universal in anti-aircraft systems, and the principle of using microwave frequencies for precision tracking rather than meter wavelength for general search became the foundation for all modern military radars. Every air defense system deployed today, from point defense missiles protecting ships to theater ballistic missile defense systems, descends conceptually from the innovations embodied in the SCR-584. The German engineers who worked on V-weapon guidance systems, some of whom were later recruited to American and Soviet missile programs after the war, eventually learned about the SCR-584 and its role in defeating the V-1. Their reactions, recorded in post-war interviews, ranged from grudging respect for Allied engineering to frustration that German intelligence had failed to identify and counter the threat. Several acknowledged that if they had known about the radar's capabilities, they would have recommended abandoning the V-1 program entirely in favor of faster ballistic missiles like the V-2, which was essentially immune to the SCR-584's capabilities due to its much higher speed and altitude. The V-2 ballistic missile, which began falling on London in September 1944, just as V-1 attacks were declining, represented a far more difficult defensive challenge, with launch speeds reaching 3,500 miles per hour and trajectories that peaked at 50 miles altitude. The V-2 was beyond the engagement envelope of any existing defensive system. No radar could track it reliably, no gun could elevate high enough to engage it, and no fighter could intercept it. The V-2's invulnerability to defense was absolute, making it a far more effective terror weapon than the V-1, though much more expensive and complex to produce. This contrast between the V-1 and V-2 illustrated a fundamental principle that remains relevant in modern warfare. Speed and altitude provide survivability against many defensive systems. The V-1's relatively slow speed and low altitude made it vulnerable to the integrated defense network that included the SCR-584. The V-2's extreme performance parameters made it effectively invulnerable to World War II-era defenses. This lesson drove Cold War missile development toward ever faster, higher-flying systems, and the corresponding development of defensive systems capable of engaging those threats. The SCR-584 project demonstrated the value of close cooperation between academic researchers and military services. The radiation laboratory at MIT was neither a pure research institution nor a military development facility, but rather a hybrid that combined the innovative thinking of academic scientists with the practical focus of military engineers. This model proved extraordinarily successful, producing not just the SCR-584 but dozens of other radar systems that gave Allied forces significant technological advantages. The post-war establishment of federally funded research and development centers like Lincoln Laboratory and Rand Corporation followed this model, creating enduring institutions that continue to develop military technology. The individuals who contributed to the SCR-584's success came from remarkably diverse backgrounds. Some were career military officers who understood anti-aircraft tactics and operational requirements. Others were fresh physics graduates who had never seen a military installation before joining the RAD lab. Still, others were experienced electronics technicians from the radio and telecommunications industry. This diversity of expertise, brought together by the urgency of wartime need, created a collaborative environment where theoretical insights could be quickly tested against practical constraints and refined into working systems. The speed of development was extraordinary by modern standards. From initial concept to operational deployment took less than 2 years, a timeline that would be considered impossible for a system of comparable complexity today. This acceleration was enabled partly by the urgency of war, which eliminated much of the bureaucratic process that typically slows military procurement. But it also reflected a willingness to accept risk, deploying systems that were good enough rather than waiting for perfect solutions. The SCR-584 had known limitations and occasional technical problems, but it worked well enough to make a decisive difference, and that was sufficient. The Battle of Britain in 1940 had demonstrated that Germany could not achieve air superiority over England through manned bomber attacks. The V-1 campaign in 1944 demonstrated that Germany could not achieve its objectives through unmanned missile attacks either. In both cases, British defensive systems, significantly enhanced by American technology and production capacity, proved adequate to blunt the offensive threat. The SCR-584's contribution to the second of these defensive victories was substantial, transforming what might have been a catastrophic bombardment into a manageable problem that was ultimately solved. The human cost prevented by the successful defense is impossible to calculate precisely, but reasonable estimates suggest that the SCR-584-equipped gunbelt prevented several thousand additional V-1 impacts on London. If each prevented impact saved an average of 3 to 5 lives, the radar system's deployment saved somewhere between 5 and 10,000 British civilians from death or serious injury. This is not a precise figure, but it provides perspective on the system's humanitarian impact beyond its military significance. The engineers who designed the SCR-584 never intended their creation to become a permanent fixture in military arsenals. They understood that radar technology was advancing rapidly and that their system, cutting edge in 1943, would be obsolete within a decade. What they created was a solution to an immediate problem, designed to be effective rather than elegant, practical rather than perfect. That pragmatic approach, focused on solving the problem at hand rather than creating an enduring monument to engineering excellence, characterized much of American wartime technology development. The SCR-584's relatively brief service life, approximately 10 years from initial deployment to retirement from frontline service, reflects the rapid pace of technological advancement during and after World War II. By the mid-1950s, solid-state electronics were replacing vacuum tubes, providing greater reliability and reduced size. Digital computers were replacing analog calculators, providing faster computation and greater flexibility, and new radar frequencies and signal processing techniques were providing improved performance. The SCR-584 had served its purpose admirably, but technology had moved on. The story of the SCR-584 and its role in defeating the V-1 threat is ultimately a story about human ingenuity responding to unexpected challenges. The radar wasn't developed to counter German missiles. It was created to improve anti-aircraft effectiveness generally. The V-1 wasn't designed to test Allied radar technology. It was built to terrorize British civilians and force political concessions. The collision between these two technologies produced a defensive victory that neither side had anticipated, demonstrating that war's outcomes often depend on rapidly adapting existing capabilities to counter unexpected threats rather than simply implementing pre-war plans. The lessons remain relevant to modern military operations. Technological superiority alone doesn't guarantee victory. The V-1 was technologically sophisticated but was defeated by equally sophisticated defenses. Intelligence failures can be strategically decisive. German inability to understand the nature of British defenses prevented effective countermeasures. Industrial capacity matters enormously. American ability to produce hundreds of radar systems and millions of proximity fuzzes provided the material foundation for defensive success, and human expertise remains essential. Even the most automated systems require skilled operators to employ them effectively. The SCR-584 radar system, developed in secrecy, deployed in urgency, and operated in combat by crews who often barely understood the technology they were using, helped save a city from bombardment and preserved British morale during a critical period. That it accomplished this while remaining largely unknown to both the German enemy and the British public it protected makes the achievement no less significant. Sometimes the most important victories are won by people and technologies that history overlooks, their contribution evident only in the disasters that never occurred because they were there, watching, tracking, and firing into the night sky. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.